We are, I'm going to be the host today instead of Hilling, who's out of town, I think. Because it's the end of the semester, we've decided to have a nice, fun talk that's going to be on the history of special relativity, and it's by my collaborator and friend, Sudipta Sarkar. Sudipta was a, sorry, I don't know what happened to my voice. Sudipta was a graduate student at IUCAD in Pune, India. And after that, that's where he did his PhD. He works on black holes and black hole thermodynamics and horizons and things like that. And then after that, he did his postdoc at the University of Maryland with Ted Jacobson. And now he's a professor at the Indian Institute of Technology in Gandhinagar. He's prepared this, he wrote to me saying that he'd been thinking about the history of special relativity. And as you can see from the pictures here, there are lots of people involved. So this should be quite fun. Sudipta, over to you.
Okay. Thanks, Maulik, for this kind introduction. So first of all, I'd like to thank all of you for giving me this opportunity. And let me first declare as a disclaimer that I'm hardly any expert on this topic. I mean, I'm hardly any expert on any topic, but particularly this topic, I am not at all even near to an expert. So this is a very amateurish approach. But Maulik told me, first of all, it's an online talk. So I have absolutely no problem. I'm not going to visit you. So what can happen in an online talk? And second, I was also told that this is last talk. So even if I say something very amateurish, I mean, people will not mind. Okay? So let me try my best. Okay. So the idea is this, the thing started is that, so few of my friends along here we have some interest in the history of science, particularly the history of contemporary science, okay, not the ancient science. And there's an advantage in, added advantage if you're interested in the history of contemporary science, because unlike the ancient or medieval science, here you can actually go and read the original sources. You don't have to learn, for example, Chinese, Latin, or Sanskrit to actually understand the manuscript. It is possible to read what Poincaré actually has written or Einstein's actually have written. Okay? So that's the one advantage. So therefore, it is easier in some sense. Okay. So, but it turns out that many of us, at least I was, and many of my friends were totally unaware that what exactly, for example, Poincaré did, or how much of the concept of special relativity was known to the people before the Albert Einstein. And for example, what was Lorentz thinking when he's writing out his transformations? So these are the issues when we were trying to understand. It turns out that it is possible to create a semi, technical version of this. So I happens to discuss with Maulik in many other things. And then he said that, why don't you go and give a talk? So that's the idea. And I'm thankful for Maulik for giving me this opportunity. Okay. So before I start again, there are these pictures of these people, mostly people with beard, except the Nicholson and Morley. It is quite interesting, actually. It is, except the Einstein, if you ignore him, all the Europeans have beard. And Michael Faraday does not. I don't know on that day what happened. But if you know all of them, if you can recognize all of them, then this talk is completely useless for you. That means you know more than relativity, probably history of relativity than me. In any case, let me try and begin. So this is all what it started. Okay, this is the first paper on relativity, special relativity, the famous paper by Albert Einstein. And for obvious reason, I'm not going to read the German version, the original version. I'm going to look at the so-called translated one. And if you look at the translated paper on relativity, it's titled Electrodynamics of Moving Body. You see the prominence of electrodynamics. It is clear that Albert Einstein, the motivation was Maxwell's equations. In fact, the first line of this paper, which I have highlighted here, it says that it is known that Maxwell's electrodynamics, as usually understood at the present time, when applied to moving bodies, leads to asymmetries which do not appear to be inherent in the phenomena. I will interpret it as whatever way you want, but it is clear that Einstein's thinking was from the Maxwell's electrodynamics. So if you really want to understand the history of electrodynamics, it's not a bad idea to first understand history of electrodynamics itself, and then particularly the history of the properties of light. So that will be my starting point. But before I go to the history, let me again give certain disclaimers, because the history of special relativity is a logical conclusion of a remarkable journey, attempt to understand one of the fundamental aspects of natural sciences, particularly the nature of motion, which is in some sense one of the most fundamental questions still antiquity. In fact, all cultures, it's quite interesting, all cultures, ancient cultures, wonder about the nature of motion in their own way. The Chinese, the Indians, the Europeans, the Romans, every culture has this fascination of understanding the motion, and sometimes very interesting fascination. Also, the story of relativity is, of course, as always for any story, is a story of several great personalities, their struggles and their egos. In fact, in the history of science literature, this is something I have realized. The history of special relativity particularly have a canonical status. So there are certain phenomena, certain changes in the natural sciences, like corpuscle to wave theory of light, or the classical Newtonian mechanics to special relativity. These are almost like canonical status. So all modern ideas about the scientific revolution uses relativity as a test case. So you can think of this as like a simple harmonic oscillator for history of science. In fact, there are very, very interesting quotes from philosophers of science. And here is one from Thomas Kuhn. Thomas Kuhn is one of the pioneer philosophers who wrote extensively on the structure of scientific revolution. That's a famous book. And I strongly recommend it to you, if you have not looked at book, to look at it. It's very exciting, sometimes very confusing, and sometimes also controversial. But it's quite interesting for a physicist to, in fact, Thomas Kuhn was a physicist. So, and in fact, very respectable physicist. So one of the very interesting quote of Thomas Kuhn is that the last quote, it says, to make the transition to Einstein's universe, the whole conceptual wave, which stands as space, time, matter, force, and so on, had to be shifted and laid down again on nature whole. So you can understand that, as you're saying, and all of you will agree that this was a conceptual revolution, and therefore the Newtonian concepts of what do you mean by what the meaning of the very word mass has completely changed from Newtonian physics to the Einsteinian physics. Again, following Thomas Kuhn, one has to be careful again that when you compare competing ideas in science, okay, one has to be careful that it is not always possible. Certain questions make sense in certain paradigm of science. I'm using the word paradigm rather loosely. Historians of science will take a lot of issue on this. But the idea is that sometimes you have to be careful when you pose questions comparing to different sets of paradigm in science. For example, you have to be careful when you say in what sense Newtonian physics is different from the Einsteinian physics. For physicists, working professional physicists, there is something called experiments, fortunately or unfortunately. So we can actually do experiments and understand which one is closer to the scientific truth. But for a philosophical point of view, there are interesting questions, okay? There are questions, for example, whether the scientific revolutions like relativity, are they gradual or accumulative, or a sudden discontinuity in the space of ideas? So philosophers of science are worried about these questions, and I will make no attempt to answer any of these questions. I just like to point out that these questions are important when you study any ideas. Also, the another important point, which I will like to point out, is that sometimes we will see that many of the ideas which we know as a consequence of special relativity, for example, the universality of the speed of light, variation of mass with velocity, all these ideas were actually known even prior to Albert Einstein, including the fact that mass should change with velocity. This is actually remarkable. But to understand these ideas, there was no theoretical paradigm. And I will mention a particular case called Weber electrodynamics, and you'll see why it is so interesting. So therefore, let me mention that the notion of paradigms, the theoretical model, to understand experimental data is extremely important when we talk about scientific progress. It has nothing to do with experimental science versus theoretical science. Therefore, I have to be very careful when I make this statement in front of my experimental colleagues. It means that even while doing experiment, what to measure and how to interpret numbers, you actually require some form of paradigm, a model, a construction of ideas. You can call it whatever you want. Without that, the numbers may not make sense. And you will see why, and I'll give an explicit example why this is important. Of course, before going to the relativity, let me tell you, and there is no point in spending much time on this slide for this audience. We trust special relativity. We trust special relativity in every day. Every day, people switch on GPS technology or sun supercollider or LIGO interferometry. We are doing a test of Lorentz invariance. Lab test in interferometry, quantum optics experiment, atomic physics experiment, all of this experiment have tested special relativity up to a very high accuracy. There are astrophysical experiments which shows that the velocity of light is independent of its wavelength up to a very, very high accuracy. In fact, some of the recent observations of the Fermi satellite put constraint at the Planck scale for certain model of the Lorentz violation of Lorentz invariance. So these are extremely important tests, and therefore it is almost clear that up to a very high energy scale in nature, the nature is Lorentz invariant. There is no doubt about it. Okay, so therefore we trust special relativity. With this, I will start the historical part, and first I will start is obviously with the history of electrodynamics. So I was looking for what is the oldest mention of something magnetic in known historical documents. So then I found this book by Robert Temple. It's called The Genius of China. It's actually quite interesting book. So it talks about scientific progress in ancient China, and it's a easily readable book. And if you're interested, please look at it. And this book mentioned of a very ancient book in Chinese culture. It's called the Book of the Devil Valley Monster. Of course, I don't know the original Chinese name. It's around 4th BC. Of course, the timeline is a little bit debatable. You take plus minus 1 BC as an error bar. But what is interesting is that there's this quotation which says that people of Cheng go out to collect Z, and when they go out, they carry a south pointer with them so as not to lose their way. So the book mention of lobestone people carry, and these lobestones are south pointer. Look at the very interesting cultural difference. They're not talking about north pointers, they're talking about south pointers. So this is probably the first mention of something magnetic in at least the written verifiable history. But nevertheless, from antiquity, we know about static electricity. The phenomenon like lightning strikes, St. fire are well documented in every ancient and medieval literature. For example, around 600 BC, there are write-up people have verified in ancient Greek, which talks about the rubbing the fire on various substances such as amber would cause the attraction of the dust particles. And we did this household experiment when we were kids. In fact, what is interesting, this is something interesting to know, that the classical names of amber, which comes from the Latin electrum and the ancient Greek word called electron, they are connected to the modern English words electricity and magnetism, and electricity and electric. So you see that this this very idea of static electricity in the how do you get it through the resin or the amber material, this is there even in the name of this word electricity and electromagnetism. But the modern scientific study of electricity and magnetism is started with this guy called William Gilbert. William Gilbert is a very, very interesting person. In fact, in the history of science and European Renaissance, it's a very, very important person. Generally, the credit of scientific Renaissance is given to these Bacon brothers, Francis Bacon and Robert Bacon. But even before the Francis Bacon, the William Gilbert, in his famous book called De Magnete, he was a court physician of the Queen, and he played a very important role in creating an intellectual circle around him. And he also has a very interesting relationship with Francis Bacon. So it was the William Gilbert who actually started the first modern study of magnetism. In fact, the first suggestion that there exists a relationship between electricity and magnetism came from a German mathematician who is residing in Russia. His name is Franz Appius. He's actually another interesting guy. So he used to believe that everything was related. It's like those days, these medieval ideas, philosophical ideas. But he thought that, look, here is a force, there is an electrostatic force and there is a magnetostatic force. And therefore, all forces are related and there must be some relationship between electrostatic forces and magnetostatic forces. And I have read a few of his quotations translated into English, and these are very, very interesting that he was thinking like all forces should have a universal force. I mean, of course, these are nowhere near to the modern idea, but still quite provocative. It was, in fact, Franz Appius who introduced this notion of electric and magnetic fluids in bodies. So the idea is that this attraction, because there is a fluid which goes, the positive and negative charges are like, in positive charge, you have some excess fluid, and negative charge, you have some less fluid. In fact, but it was the Hans Christian Ørsted in Copenhagen who actually first started the experimental demonstration that there must exist some relationship between electricity and magnetism. So what he did is that he took his compass on a current carrying wire, and immediately the compass was deflection. He already knew that compass shows deflection in the presence of magnet. Now he sees that compass also shows deflection in the presence of a current carrying wire. So therefore, there must be a relationship between magnetism and electricity. So I was looking for that, why the hell Ørsted put a compass in front of an electrical current carrying wire? I mean, generally, why would you do that? So it seems he was motivated by another guy called Ritter. He was also a physicist who was also completely convinced that there must be a relationship between electricity and magnetism. And he suggested Ørsted that why don't you do this experiment through a letter? At those times, there was, of course, no email. And then Ørsted actually did the experiment. And immediately after Ørsted, it was Ampere who first attempted a mathematical theory of electromagnetism. So the Ampere's law before the Maxwell, it was started after the experiment of the Maxwell. And then, of course, in 1931, Faraday discovered the laws of electromagnetic induction, and then the familiar story of electromagnetism started. Okay. So this is, in some sense, one slide summary of the history of electromagnetism starting from William Gilbert. So although these are all well known, now let me bring to you a very interesting person called Weber. Now, William Edward Weber was a German guy who used to live in University of Göttingen. And in fact, at the time of the Gauss, in fact, he was a colleague of Gauss. Okay. In fact, they worked on some project together also. So he wanted to say, notice that there are these laws of Coulomb's, which says that the force must be proportional to the product of charges divided by distance square, blah, blah, blah. But he also found that Ampere's has given a law where the force is some sense is proportional to the current. And that you immediately can understand. You think of two current carrying wire, and those two current carrying wire has a force proportional to the product of the currents. And therefore, he says that there must be, the Ampere's force law seems to suggest that the force between current carrying wires is proportional to the velocity of the charges. Again, Faraday at that time also was given an EMF rule which says the force is proportional to the change of current, di dt. In Weber interpretation, that become the acceleration, because I is like a velocity, di dt is like an acceleration. So just like a pure phenomenologist, he said that, okay, I can combine both the Ampere's law, Faraday's law, and Coulomb's law into one force expression. And what will be the force expression? He said, I will write a force expression. The first term will be the Coulomb's law. Second term will be some constant into proportional to velocity, which will give me the Ampere's law. And the third term will be acceleration. And not only that, what he says that I will choose this constant K1 and K2 such a way that this force arises from a potential, because he wanted a conservative force. Understand that there is absolutely no notion of field at that time. So he thought that when a particle moves in electromagnetic field, I'm using the modern language, the momentum, everything must be conserved. So he's looking for a conservative force. Of course, today we don't use conservation on the particle itself because the field also has to be incorporated to the picture. But this is well before the Maxwell's electrodynamics. And then he wrote down this equation. This is the equation which is called the Weber force formula. This R is basically the relative separation between charges. And here I have introduced this word, this 2c square factor. So forget everything that c has anything to do with the speed of light. And it will be actually to do with the speed of light. If you look at original Weber formula, he gives only r dot square by c square. I have changed it to 2c square, so that this c is actually same as the velocity of light. And this is a conservative force. You can find a velocity dependent potential for this force. Okay, very good. So now the Weber says, okay, this is my unified force law, which combined all the laws of electrodynamics. Now the struggle was, how do you estimate this constant c? Of course, the obvious answer would be you have to do some experiment. Now look at the modern notation. In modern notation, if I use the word epsilon 0 here, which is basically SI unit, but I set mu 0 equal to 1. So from SI unit, I go to the what is called the electromotive unit. So there are these different unit systems in electrodynamics at the end of the Jackson. So then this c square, according to Weber, is nothing but a conversion between electrostatic unit of charge to the electromotive unit of electricity. That's all. So and he said that I will want to measure this constant. And then in 1856, he went for an experiment in collaboration with another guy, Rudolf Kohlhaas. And what they did is basically they took a capacitor and the jar, and then what they do is that they charged and discharged the jar. So idea is that they charged with a precisely known amount of electricity in electrostatic unit. And then when they discharge it, they measure what is the exact amount of current is coming out. So they know the conversion between electrostatic and the electromotive unit. And that gave them the value c square. And if you look at their paper, this is the value they have given. They have given it actually miles per hour. I have converted into meter per second from their original paper. Any student of physics today, if they look at these numbers, immediately would say, oh, this is the speed of light, 10 to the power 8 meter per second. What is quite interesting is that although the speed of light is very well known at that time, very well measured by the experiments like Foucault, or even before that there was the experiment by Rommel, observation by Rommel to the moons of Jupiter. But neither Weber nor his friend realized this number has anything to do with the velocity of light. If you look at this paper, he has mentioned that this looks like a velocity, but he never equated it with anything with the speed of light. Okay, this is just 1856. So if you talk to Thomas Kuhn, he could argue that, look.
Wait, is that because you put in that square root of 2?
Well, it just changes the factor. For me, 10 to the power 8 is everything.
Okay, but so you said that they had it without the 2 there.
Oh,
so
don't have that 2. Yeah. But I think 10 to the power at the error bar of the speed of light will allow you to only to, at that time, 10 to the power 8 meter per second. Rest, I'm not sure very. So the Kuhn would argue, so here I am arguing in place of Kuhn, that they did not have the correct theoretical paradigm to understand this experiment. So the idea is that this experiment, to understand this experiment, you also actually require a theoretical paradigm. The theoretical paradigm which this guy Weber was using is actually a action at a distance paradigm, where there is absolutely no reason why a propagation velocity will become. And therefore, he completely missed that fact. This experiment is very well described in this book, Story of Electrical and Magnetic Measurement. And this is a very nice book which talks about a lot of experimental breakthroughs in the history of electromagnetic theory. But today, the person who actually understood the meaning of this C is, of course, the James Clerk Maxwell. This is the famous book by Maxwell, and Maxwell wrote down in so note that Weber is in 1856. Within 4 years, Maxwell wrote his famous paper. And this paper successfully provided a mathematical theory which connect electricity and magnetic phenomena. And we all know this theory very well, so I'm not going to waste any time on this. But I should say the modern version of, so if I don't know how many of you have looked at this book, I strongly encourage to look at this book and then just close it, don't read it. It's unreadable, this book, the treatise on electricity and magnetism, because he uses the notation of partial derivative and everything without even using anything like Nabla operator or the del square operator, and everything is horrible. Okay, I've actually tried to, the only chapter which is probably most interesting is his discussion of the displacement current, where he brought out displacement current from the etherical point of view. But we should be grateful to a person called Heaviside, who actually translated Maxwell's obscure notation into the modern notation. So the modern notation of vector calculus which you use is actually due to Heaviside, and Heaviside will also play important role later when we'll talk about the contraction of the bodies when they move, the so-called Lorentz contraction. So there is a very interesting letter Heaviside wrote to one of his friends, and if you read that letter, basically what he is talking about, I have not understood anything from the Maxwell's paper, so I completely rewrote the Maxwell's equation into my own language of mathematics. And thankful to Heaviside today, we can read Maxwell's paper very easily. But Maxwell's equation produced a remarkable result. Okay, these equations predicted the existence of the electromagnetic wave. So I actually wanted to know what actually Maxwell wrote when he figured it out that velocity of light is arising in his equation. So this is this exact quotation from this paper, The Dynamical Theory of Electromagnetic Field. And it is quite interesting to read this quotation. So let me read it for you. Hence, the velocity of light deduced from experiment agrees sufficiently well with the velocity of v deduced only from the only set of experiment as we yet possess. Now, let's see what he is right. The value of v was determined by measuring electromotive force with which a condenser of known capacity is charged, and then discharging the condenser through a galvanometer so as to measure the quantity of electricity in electromagnetic measure. So what he is talking about, that the same experiment by Weber, the only use of light made in the experiment was to see the instrument. So that's a very interesting phase. He's saying the only use of light means I'm just seeing it. Next he says the value of v is the velocity, found by Foucault, was obtained by determining angle through which the revolving mirror turned. This is a very famous experiment by Foucault. And no use whatever is made of electricity and magnetism. So what he is saying is that the measurement of the speed of light by Foucault is completely independent of electricity and magnetism. And the deduction of the velocity of light from his set of equations is completely independent of the optics. So therefore, the fact that these two velocities are exactly same must be very profound. And rest of the argument is exactly same, almost same as the way modern day we actually present things, apart from the mathematical notation. Maxwell's equation clearly established that the electromagnetic disturbances travel at the speed of light, okay, and light is an electromagnetic wave. Although it took several years to come up with this, but this is the beginning. Now, here I should go to the nature of the light. The understanding of the light is as an electromagnetic phenomenon is in itself is a revolution in science. In fact, light as a wave is not at all a new concept. In fact, it was clear from the Young's double-slit experiment more than 50 years before Maxwell that light has a wave nature, and also from the subsequent study of interference and the diffraction. But the history of wave nature of light is also quite important and quite interesting. So, for example, we already know about other waves in nature. See, it's not unnatural to say the light is wave. So its question is why people like Newton held to the corpuscular notion. So for example, we know about sound wave or general elastic wave in the matter. Sound waves are longitudinal, particle of medium through which the sound is transported. They vibrate parallel to the direction. So the contraction and the refraction and the sound wave moves on. In fact, even in 17th century, it was clear that if light is a wave, it cannot be longitudinal. And this is quite interesting. Even in 17th century, in fact, people have found the double refraction of light in a calcite crystal. So this is a calcite crystal, and you clearly see two rays of light, two images. One is so-called the extraordinary light, and the other is the ordinary light. And it is this is this discovery which led to the discovery which is called the polarization light, which I'll discuss, and which shows that light cannot be a longitudinal wave. Why? Because immediately there are experiment people did. In fact, Newton himself did some experiment that if you take two calcite crystal and if you put them a certain angle, you can stop the transmission of light through them. These are like Polaroid plates. It is clear how it is possible that if light is a longitudinal wave, just by changing the vertical axes or orientation of the crystal, I can stop the longitudinal propagation. The concept of polarization has an interesting history, and this is related to the Newton's corpuscular model of light. You remember that a study of reflection and refraction convinced Newton that light has a mechanical property. See, if you read the literature at that time, it is clear that that literature at that time, particularly scientific literature, is heavily influenced by so-called mechanical view of the universe. Everything has to be like a mechanical clock. Everything has to be, can be explained like a motion of billiard balls. Okay. So Isaac Newton tried to explain the phenomena of double refraction by assuming light rays have sides. So this is quite interesting. In fact, in his book, Optics, Newton used the idea of double refraction or the polarization, that what came later, to argue against the wave theory. Because Newton says all waves are longitudinal. We never heard of transverse waves. So it is clear the light cannot be longitudinal. So it's clear that that has to be then understood by a corpuscular model. One chapter of his book, Optics, was entirely devoted on double refraction, where he tried to explain double refraction and use it as a telltale evidence against the wave theory of light. So how did Newton explain double refraction? So according to Newton, that light particles have their own axis. So non-polarized light, in Newton's view, is that axes have arbitrary direction. And then what Newton used to think, if you read the Optics, is that there is a preferred direction of this crystal, and the light's particles also have a preferred axis. When they match, the crystals allow the light particles to move. This is quite interesting. I don't know what to say about it, but it is quite interesting to know that the double refraction was one of the major evidence cited opposite to the wave theory. So the Newtonian corpuscular theory was taken into mathematical completion is by a guy called Louis Mose, a French engineer. In 1810, there was a famous competition. That competition was to mathematically prove, whether the corpuscular theory or the wave theory of light, which one is the correct theory. Okay, this is like proving whether the string theory or loop quantum gravity is the correct theory through a competition. We don't do that nowadays. Good for us. But interestingly, Morse won the prize, where he proved that the theory of corpuscular theory can successfully explain the double refraction. Okay, so in some sense, he claimed that he has proven the double refraction, at least the corpuscular theory, theoretically. Okay, and the idea, what he uses is again the idea of Newton's, but he also uses some preliminary concept of mathematics of least action. He uses actually geodesic motions. Then I'm still trying to understand his paper, but that's a side remark. One important point is that Morse said that the light particles have sides or poles. This is the extensions of Newton's idea that light particles have axes. And this is the first time the word polarization is used. The word polarization came, it is completely a corpuscular concept, that the light particles have their poles. Okay. But of course, it turns out this so-called competition is completely meaningless. It was immediately clear within few years that the discovery of interference and diffraction, the corpuscular theory cannot explain this. Even the refraction, the ratio of the speed through denser and the rarer medium, we know that corpuscular theory cannot explain this. And that led to the an almost universal acceptance of the wave theory of light, although things are not as quick as I am mentioning. There was interesting battle between Laplaces and Fresnels in the French Academy, the politics of French Academy. There are host lot of literature dedicated to this transition, but that's a separate story. But this immediately led to a puzzle. The puzzle is that wave requires medium to travel, but transverse wave cannot travel to elastic medium easily. Because we already know that light cannot be a transverse wave. Light cannot be a longitudinal wave. It has to be a transverse wave. Then immediately it was not even clear how come light travel in an elastic medium. There's a very interesting letter exchange between Fresnel and Poisson. So let me just give you some background. Poisson was the person, is the same Poisson as the Poisson's ratio, who derived the theory of elastic wave propagation through a medium. And when he noted the wave theory of light, and he was totally confused that how can a transverse wave travel through a medium? Because the direction of motion is in the transverse direction. This motion, there is a viscosity in the medium. How can the energy travel from one point to other point? And then he wrote these lines to Fresnel, and one line I just wanted to read to you. It is thus impossible that the molecules, even if they're initially moving perpendicular or inclined to the rays of the waves, could conserve such direction as has been supposed in order to explain the singular phenomenon of non-interference of the rays of light polarized in perpendicular direction. So basically the idea is how can light travel if they are transverse direction? Because there's a viscosity. So the Fresnel's reply is quite interesting. There's this only part of the reply I have written, and there's a long reply. If you actually read that reply carefully, it's basically saying shut up. So basically Fresnel was saying, look, I don't know. All the experiments suggest that light has to be a wave and it cannot be a longitudinal wave. So there must be something wrong. We must have come up with some new propagation theory. But you cannot fight with the experimental result. You have to accept light is a wave. Fresnel actually does not give any satisfactory answer to the mathematical, the real, objections by Poisson. But these letter exchanges are quite interesting. Well, the many phenomena indeed compelled us, including the Poisson, to accept with a little bit of doubt that light is a transverse wave. But then the question is, of course, what is the medium? And this hypothetical medium was given a fabulous name, and the name is the so-called luminiferous ether. So I was looking for what is the first time ether word is mentioned in a recorded scientific discussion. In a scientific discussion, not in a mythology, some other mythology or something other thing. So I found there's a letter from Newton to Robert Boyle, is as old as 1678. So Boyle asked Newton in certain, certain ideas about gas and mechanics and molecules and everything. And then Newton write an official reply. And this letter is freely available. You can search in internet letters to Boyle by Newton. Okay. So this is what Newton writes. If you look at the letter, it says that I shall set down my appreciation in the form of supposition as follows. And first, I suppose that there is diffused in all spaces an etherical substance capable of contraction and dilatation, strongly elastic, notice the spelling, that is Newton's spelling, and in a word, much like air in all respect, but far more subtle, unquote. So this is the Newton says that before I explain everything about the mechanics, I will assume that this ether exists, which is far more subtle than even the air. Okay. In Western mythology, the word ether is very well known. In fact, it's kind of quite apparent in the Greek mythology. Ether is the personification of the bright upper sky, is the son of darkness, brother of the day, and what is in Orphic or the old Greek cosmology theories. Ether is the offspring of time and the brother of chaos and whatnot. There are interesting poems dedicated to the ether god, and there is this in famous museum of this is in which place? This is in Athens, the Museum of Western Art and Form. There is a famous statue where the ether, Lord Ether is fighting with a demon with lion head. So in Western mythology, the word ether is well known as something subtle, some fifth element. And this was there even in the mention of philosophical writings of old Greek philosophers. So the experiment with light demanded, once it is clear that light is a transverse wave, the ether has to be a fluid in order to fill the space, but one with millions of times more rigid than steel in order to support the high frequencies of light waves. It also has to be massless and without velocity, otherwise we would have noticed it in the motion of planets. Additionally, it also appeared to be completely transparent, non-dispersive, incompressible, and continuous in very small scale. These are impossible properties. So there is a small joke by Lord Rayleigh. I don't know whether this joke it's like a typical British humor. It says that it has been said, someone sarcastically, that the ether was made in England. This statement is an exaggeration of the truth. I might even argue that it was largely constructed in the Royal Institution. So that's a very Lord Rayleigh typical. But then if you want to know what was the scientific way of looking at ether, there is a very interesting encyclopedia article which Maxwell wrote in 1878. That article is a very interesting article of the relevant view of ether from the physicist at that time. And there is an interesting quote where Maxwell says, ethers are invented for the planets to swim in, to constitute electric atmosphere and magnetic effluvia, to convey sensation from one part of our body to another, and so on. And then he concludes, the only ether which has survived is that which was invented by Huygens to explain the polarization of light. So it is already clear that the theorists were not very happy with the ether. In fact, if you look at this encyclopedia article by Maxwell criticizes all form of ether and saying that these are not tenable properties. There is nothing known in the theory of matter at that time for which this will be a tenable property. But nevertheless, he accepts at the end of the article that we still need something like ether to explain the propagation of light. Okay. So therefore, now it is the challenge is up to the experimentalist to detect the ether. So there is okay. So the point is that there is a side story with the Galileo's idea of ether, Galileo's motion, which I'll skip. It's not very important. But of course, the idea was that once the Maxwell's equations are invented, the people tried to understand that how we understand the notion of light, propagation of light, and the Maxwell's equation together. But it is almost clear that Maxwell's equations will be in conflict with the notion of relativity at that time, so-called the Galilean transformation equation. This is a textbook stuff because Maxwell's equation immediately give you a notion of velocity, and the question is that which frame you are talking about. So it will be interesting to ask this question that is there a frame in which the velocity of light is the velocity of light, and what kind of modification of Maxwell's equation required when you go from one frame to other frame? Nevertheless, the first person who actually asked this question, how one can find a set of transformation equation which leaves the velocity of light invariant, not in this exactly the language, is a person called Holdemer worked. He was a German physicist, and the answer he got is actually quite interesting. So let me go to that answer. So Vogt was a pioneer of piezoelectricity. He was a German engineer. He was studying Doppler effect in 1887. This is the time when Maxwell's equations are already derived, understood. The wave equation of light for the electric and magnetic field is known, although in some obscure notation. So what Mr. Vogt wanted is to derive Doppler effect for light. So how do you derive Doppler effect? You write down a plate wavefront, and you wanted to know to the frame of the moving observer. That means you do a transformation equation which leaves the plane wavefront plane. And then you figure it out how the frequency is changing. And from there you get the relationship between the frequency in the moving frame with respect to the original rest frame. So he did the same calculation with the light, with the wave equation for light. So in modern language, he was looking at the covariance of the homogeneous wave equation. And he immediately found a set of equations instead of the Galilean transformation equation. And in fact, he understood that Galilean transformation equation is untenable here. And the set of transformation equation he found are of this type. So this is notation written in a little bit, give me a second. There's something going on here. Okay. Written in a little bit different notation. So in modern notation, these first three equations are nothing but Galilean equation. The last equation is T prime equal to T minus Vx by C square. This omega is like a C. Okay. So immediately Vogt understood that the last equation demands that the time must transform. The universality of Newtonian time must break down if we want covariance of the homogeneous equation. Of course, this equation is not same as the Lorentz equations. If you notice carefully, it missed a factor gamma. This equation don't form a group. So if you ask what is this equation in a non-modal language, this is actually an equation which leaves the metric invariant up to a factor. But that factor is actually gamma square. So it's kind of a conformal transformation, which leaves the metric invariant up to a factor. So Voigt actually wrote there is an interesting conversation between Voigt and this guy, Lorentz. So when Lorentz first found his equation for completely different methods, Voigt actually wrote him a letter. It's kind of a cite me request, where he says, look, you have found this equation, but I have also found this equation 10 years before you. Lorentz actually acknowledged it, and he actually wrote back a reply that, okay, no worries, I will cite you from subsequent papers. And in fact, he has actually included the reference of Voigt in his subsequent papers. So this was pre-archive days and long before archive days. So the first person who actually tried to measure the velocity of light with respect to ether is an engineer, French engineer, Fizeau. It also has a very interesting story, but let me not go into it. What Fizeau did is very simple. He measured the speed of light through a fluid when the fluid is moving away from the speed of light and towards the speed of light. That's all. So this is a fluid which is moving in this direction. You send your light through a mirror like this. In this part, light is moving opposite to the direction of the fluid. And in this part, light is moving towards you again in the towards the direction of the fluid. And you take these two light, you interfere them, and you look at the interference fringe. So if there is any difference, you should see a fringe width shift. And in fact, you can see a fringe width, and this is something called the Fresnel's drag coefficient, where n is the refractive index of the fluid. So what is quite interesting, put n equal to 1, the vacuum, and you immediately see the drag coefficient vanish. So this is clear that at least the vacuum, when the light moves, it does not drag the ether along with it. There is no ether drag. So at those times, there are a lot of literature on this. Note that all this effect are V by C effect. So it was conjectured at that time, look, no, this is because maybe the effect is only there in the V square by C square, like the typical physicist argument. If it is not you see in the first order, you should go to the second order. So the people convinced that you should go to the second order, V square by C square, and to see the effect of the ether. Now it is not easy to go to the second order because you need more sensitive instrument. You need to go for a round trip of light and do an interference. And the person who could able to do it is actually the other side of Atlantic. There's Michelson and Morley, first American Nobel laureates. And they do this pioneer experiment with the interference fringes. I will not spend any time on that. That we already know that what they show, Michelson and Morley experiment, that even in the second order, V square by C square, there is absolutely no proof of the presence of ether. The speed of light is universal in all directions, and that led to this letter by Michelson to the Rod Rayleigh, and you can read that letter, the particular quotation. And basically the quotation says that within the experimental accuracy, we could not able to detect any fringe width. And this is the most famous failed experiment. All the experiment failed to detect any evidence of the ether. And therefore the ball is again back onto the theorist. So it is the theorist which was forced to invent the concept of ether They gave it to the experiment to detect, and the experimentals could not able to detect with all the possible modern technology, and the ball is back to the theorist. Here comes two very, very pioneering theorists. One is a mathematician and other is a physicist who took up this challenge. So the idea is that how do you even understand this experiment within the presently known theories? And two extraordinary people, Henri Poincaré, who was a great French mathematician, and Henrik Lorentz, who was a physicist, both of them tried within this short time period, 1890 to 1995, even few days later also. No, I mean, relativity was not always immediately established at 1995. They suggested approaches to explain all this apparently contradicting result. The main idea behind all these approaches was to design a theory of matter, charges, and electrons. So let me go back to what they have tried. The starting point of their theory was an observation by Heaviside. This is the same Heaviside whom I was talking about regarding the Maxwell's equation. Heaviside also could able to integrate the Maxwell's equation and found the electric field due to a uniformly moving charge. This is a first year UG, we derive it by using relativity principle, but you could have derived it without even mentioning relativity by directly integrating the Maxwell's equation. This is exactly what Heaviside did. Now there is this curious factor of 1 minus v square by c square in this derivation, in this electric field. Heaviside immediately understood that if you take the ratio of the electric field towards the direction of motion and the perpendicular to it, there is this factor minus v square by c square whole to the power 3 by 2. That means the electric field around a moving body, even if the body is symmetric, is not symmetric. There is an asymmetry of the electric field. By looking at this formula, Fitzgerald wrote a very short.
Sudipta, how did the C enter this formula?
So I have written it there C, but in their notation they contain mu0 and epsilon 0.
Yeah, but so
in their original notation, they contains all this. See, C is already there, even in the Maxwell's relation also.
No, I understand, but I mean, so you start with Coulomb's law here, and then
so you start with the Maxwell's relation. 4 box mu equal to j mu.
Okay.
And you just integrate it.
I see.
But you don't write it box.
Yeah, sure.
In fact, it comes from what is called the Zerifenko equations in Griffith.
Yeah.
That's all. Yeah. So C is basically 1 by square root of mu0 epsilon 0. So then Fitzgerald wrote a short letter in the Science magazine where he said, look, because of this asymmetry, now suppose the body, so this is very strange that they were thinking of body made up of charges, everything. Even if you take a spherically symmetric body, it contains internal charges. And because of asymmetry of this electric field, there will be a back reaction of the electric field on the body. And this back reaction will also be asymmetric. So the claim was, because of this asymmetry back reaction, the body will either contract or expand asymmetrically. So it's a very interesting idea that the molecular forces, see at that time, every force was electrical in nature. Okay, there was only 2 forces known, electrical and gravitational forces. So the idea was the molecular forces will be influenced by this electric field and they will have asymmetric proportions and that will lead to a contraction. And this started a new set of ideas, justifying the length contraction from the theory of matter. This is the beginning. In fact, this is the path which Lorentz followed and later also Poincaré. Lorentz immediately understood there is a set of transformations which automatically give this contraction. And he wrote those transformations. See, Lorentz transformations are not derived. Lorentz never derived transformation by demanding speed of light is constant. That is exactly what Einstein did in his original paper. Lorentz was looking for a covariance equations for Maxwell because he wanted to derive this transformation which will automatically give him the contraction. Also, he went ahead, used this idea of length contraction through charged matter, create a theory of electrons. So actually, it's quite interesting to read. I'll give you the good reference to read this. So the idea was that matter is made out of charges. Of course, the electron word is not used at that time, although J.J. Thomson has later, I don't know at what time he sees the electron. So matter is made out of charges. Whenever matter moves, the electric and magnetic field back react on these charges. And that is the way the contraction takes place. That is the overall picture. And the light from the matter is basically an electromagnetic phenomenon arising of the charges. What is the experimental proof of this? So it turns out at that same time, there's a famous effect, which is called a Zeeman effect, which was discovered. What is Zeeman effect? You take the spectral lines of the sodium, D1, D2 line in modern notation, and you place them in magnetic field, you immediately see the lines are split up. Today, we call them the spin-dependent anomalous splitting. Forget about it. So basically, Lorentz immediately saw this experiment as a proof of his theory. Why? Because he wrote, note what he's trying to understand. In his picture, everything, even the light, is a consequence of the electric and magnetic field and the charged matter. If you now put the matter in front of a magnetic field, this charged particle will deviate from their path. And according to him, as a result, it is obvious that this spectral lines will broaden. In fact, this is the work where he first wrote down the Lorentz force law, because he wanted to equation which actually describe how the charged particle will be influenced by the electric and magnetic field both at present. What is quite interesting is that Lorentz and Zeeman was awarded 1992 Nobel Prize for his theory of electron. So there's a Nobel Prize given to Zeeman and also to Lorentz. So it seems Lorentz never able, sorry, that Zeeman was not well and he could not able to attend this Nobel Prize ceremony. Lorentz nevertheless went and he gave a Nobel Prize lecture. Any of you who are interested about the pre-relativity physics, what was the view of Lorentz on the theory of electron? This Nobel lecture is the reference to look at. This is exactly at 1902, where he is describing what he did as a theory of electron. At the same time, Poincare was beginning to ponder about the nature of relativity principle and ether. So note that Poincare was already a leading European mathematician, but his contribution to relativity is a little bit difficult to assess. In fact, there is a lot of debate as late as 1950 about what was the Poincare's actual contribution. In fact, there was a guy called Whittaker who actually demanded that it was Poincare who discovered relativity. And it was not just any acquisition, because it was Max Born who actually, refuted the writings by Whittaker in 1954, almost at the same year where Einstein died. So it was a serious debate in the history of science. If you read Poincare's article, it's very difficult to understand. I tried myself, but it's quite difficult. But it's also clear that he is the first person who proposed the principle of relativity as a physics principle. Some of his quotation is quite clear. He was the person who actually derived correct Lorentz transformation. In fact, Lorentz original derivation has some error. Not only that, both the Poincare group and the Lorentz group are actually due to Poincare. The group property of the Lorentz transformation was first proven by Poincare. Obviously, he is probably the only person among the physicists who know about what is a group at that time. Physicists probably have no idea. But nevertheless, he actually attempted, analogous to Lorentz, an electromagnetic theory of matter. His aim was to postulate an electromagnetic theory along with some non-electromagnetic matter. I'll explain it immediately. But the path was exactly identical to what Lorentz was thinking. So what was the path?
Sudipta, we're sort of out of time, but we started
I'll just finish
late
it.
and let's try to wrap up here. But
so basically the idea is, again, Poincare goes ahead and he wanted to figure it out everything in terms of the electromagnetic back reaction. And there's a very interesting idea, something called fourth-third problem in electrodynamics. And Poincare created some kind of negative energy stress akin to the today's, you can call it similar to the cosmological constant. And when you add this, you give the correct factor and everything comes up. But the main idea is that he understood that the electromagnetic energy renormalizes the mass. That idea was already there in the Poincare. So they understood the infinity of the self force actually affect the mass. And from there, they predicted mass should depend on velocity, because the electromagnetic energy contains this 1 minus v square by c square factor. I can explain it later. So let me go ahead. I will not go into the mathematical detail what exactly Poincare did. But if you're interested, there's a very interesting paper by Damour, the same Damour of the general relativity and membrane paradigm. So there's a paper which is written in French, and also the English translation is available, where he reformulated Poincare ideas in modern notation. And it's a very interesting paper to look at. So basic idea is that this equation, m equal to m naught by square root of 1 minus v square by c square, already there in Poincare's calculation. He understood, and in fact, they predicted how the mass would change its velocity. Nevertheless, in fact, there are experimental results were announced which particular type of mass should change its velocity. Nevertheless, it was nothing to do with the relativity. The motivation was completely to find the theory of matter. So let me go ahead in last two slides. Of course, 1995, it is this Anna's anomalies, the famous part. I will not use this quotation by Einstein. We already know that Einstein's motivation was totally different. It has nothing to do with the theory of matter, unlike the Poincare or Lorentz. And Einstein's motivation was to understood the everything like length contraction, time dilation as a measurement process, already as a logical consequence of his postulates. And then the only interesting question is how Lorentz actually, considered Einstein's contribution. It was clear Lorentz accepted Einstein's with open hands. Okay, he accepted that his motivation was wrong. He accepted that Einstein's motivation was extremely novel, revolutionary, and there is no doubt that Einstein's led to a complete revolution in the foundation of space, time, and motion. So this is clear in all his quotations. But what is interesting is the quotation by Poincare. So the last quotation, I should say, it is 1912, as late as 1912, Poincare gave a series of lectures in French Academy. And then he says, in all instances, it differs from that of Newton, the mechanics of Lorentz endure. So even as late as 1912, Poincare calls this new mechanics as the mechanics of Lorentz. There is no mention of Einstein. So in fact, in 1914, Poincare died. So we don't know what would have been the Poincare's detailed thing to the. So what we can conclude from the history of special relativity, it's a classic example of scientific revolution. It's a paradigm shift in our understanding of the universe. The process of science is a gradual, painstaking process. Individual plays their important role, but the continuity is also important. Now, what is not, so the only interesting question is that why the hell Poincare and Lorentz, who are no less brilliant than Einstein, could not able to find why their approach was totally different. So it's very difficult to answer this question. One obvious answer could be Einstein was lucky. Okay, then there is no, nothing more you can do. But there is a one possibility, interesting possibility, that note that compared to Poincare or Lorentz, Einstein was far more insulated from the contemporary scientific approach. In fact, I am ready to bet if Einstein was a professor at a German university, he would have followed probably the same approach of Lorentz and Poincare, finding another theory of matter. So it's good that he was insulated from the scientific world at that time, so that probably his independence has led to a completely different. In fact, this actually matches with Einstein's later life also. He was always independent, never caring about what the rest of the community says. Relativity, he was lucky. Unified field theory, he was not that lucky. With that, I will end. Thank you.
Thanks very much. That was a very fascinating talk. Let's thank Sudipta. And if you have any questions, now's the time.
I have a question.
Yeah.
Okay. Well, actually, two questions. One, do you think then that these major paradigm shifts, thank you, by the way, for that excellent talk with your details in that, But what about the timeline for such major paradigm shifts or such major changes in revolutionary thinking? Do you think they're getting shorter today? Do you think, maybe because there's better communication, greater number of people working on these things and so forth, that these shifts will be coming more often or a little bit quicker over time? And then the second question is, do you have any recommendations or thoughts on this for perhaps improving the rate of understanding in these types of things?
Well, let me be honest. I don't have correct answer to any of these questions. I mean, let me be very honest. I don't think anybody has a correct answer to any of these questions. These are very, very important questions. But nevertheless, let me try a little bit. As I mentioned that the Einstein's relative isolation from the contemporary scientific world, in my opinion, it has helped that he did not follow another theory of matter. Now, it seems to suggest that if you're an outsider, it's probably easier to make the revolution, but that's also a very, very wrong approach. In fact, today, physics is so technical compared to the Einstein's time, it will be almost impossible for an outsider to make worthwhile contribution in technical part of the physics. I mean, I'm not saying it is impossible, but it's very, very difficult. So the point I would say is that there is a lot of information, and most of the information is probably not very useful. Okay, it's a high entropy. But I think that the main progress of science, the nature of scientific revolutions, the general structures probably today will also be available. The only point is that whether in this huge wave of information or entropy, finding the order will be difficult. That is definitely true. But I don't know what is the prescription. You can't stop the amount of information. You can't, put a censorship on the number of papers in the archive. How many of us actually look at all the papers in the archive? We just, it's impossible. Probably if there is an epoch-making paper, there's a very high probability that me and you will probably miss it. And we'll probably know after a month or 2 months or maybe a year from somebody else. So I don't think there is any way. This huge volume of scientific revolutions, scientific information actually democratized the science. For example, for third world scientists, archive is it's such a boon going beyond the publications and the research journals, that the access of science has so much increased. But on the top of that, it has created huge entropy. So I think we have to live with it. There is no straightforward answer to this, at least in my opinion.
Thank you. Maybe we can have some computer help.
Maybe some artificial neural network or something. So, Maulik, there's a question in the...
And there's a question in the chat as well.
Yeah. So, in fact, I can suggest a very nice book, which is by this Einstein's biographer, Alexander Pies. The book is called Subtle is the Lord. By the way, that's not just the life of Albert Einstein. Okay, it's a very technical book. Books will assume that you know everything about general relativity. So it's a very good book to understand the beginning of the what happens at special relativity and what are the other things. Then there are interesting papers people have written. American Journal of Physics, for example, has nice set of papers on Poincaré and Lorentz. And I think those are very, very good reference to start with.
So it was Minkowski who realized that, there was a geometric picture of special relativity. So what was Einstein's view of these transformations?
Einstein rejected it. Einstein did not like Minkowski's view.
But what was his own view of his transformations? There are transformations in measurement.
So these non-orthogonal transformations, orthogonal axes to non-orthogonal axes, Einstein did not like Minkowski's paper at the beginning. In fact, there are explicit letters from Einstein to other friends where he says that, okay, it does not add up much of understanding. But he changed his view while after the understanding of the Riemannian, when he encountered general relativity. So the geometrization of special relativity was not Einstein's idea. In fact, Einstein never attempted it at the beginning. It was his In fact, he was almost forced into geometry by the consideration of gravity. And that is around 1908 when he started accepting that it's better to use the language of the metric. That itself is another fascinating story.
So he had these transformations on X and T that were originally from Lorentz, but now that Einstein viewed as transformations of space and time rather than of matter. Is that correct?
Exactly. So basically, so if you look at this paper here on the electrodynamics of moving body, it has no reference. There's only, it has no citation. It does not cite anybody. The only mention of a physicist is Maxwell. I don't know whether he mentioned Newton and Galileo. I have to look at it again. Okay. Well, he doesn't need to. Okay. But the point, the way Einstein's look at Lorentz transformation equation is completely different because he derived Lorentz transformation. Okay, if you look at Einstein's papers, the first 2 pages, he discusses the clock synchronization. How to synchronize clocks. So this so-called idea of Einstein synchronization. Okay, this is totally absent in any of the subsequent work. So for me, it is a clear signature that Einstein started looking at it as a point of measurement, not at all anything to do with the equation of motion of the matter. Even if you ignore the Lorentz transformation word, Einstein's mind, this first 2 pages, when you're talking about synchronization of clock, is a evidence, clear evidence for me that his view was totally orthogonal to the way Poincaré was. None of them was thinking about what is the measurement of the speed of light. How do I measure one-way speed of light versus the two-way speed of light? So I think that's a telltale evidence. If you look at the electrodynamics of moving body paper, the first few pages, Einstein discusses how to synchronize clock because he's going to discuss the measurement.
But
So
the reason he
therefore,
didn't think of it as geometrically is because
no.
Because he hadn't accepted yes the idea of space-time, actually. So he's still working in a 3+1.
Exactly.
The there's a 3-dimensional space and 1-dimensional time, but what is meant by those is frame dependent.
It is that credit goes to Minkowski. In fact, the Minkowski has this famous quotation. I can't paraphrase. I just paraphrasing it. There's from now, not the space, neither the space, not the time, but it is the space-time which is remain absolute. So the credit goes to Minkowski.
Henceforth, space and time will
space and something like that.
Shadows and only the union of the two will survive.
I don't remember the exact quotation, but it is something like that.
Well, thanks so much for your talk. We're out of time now, and great to have you.
Thank you. Thanks a lot. Okay, see you.